Okay, let us continue the fourth part of today's class. Okay, please see the slides of chapter 1. So we have derived these two equations, equation 1.13 and 1.14. And finally, we get GD is equal to ND. That is, the diversity gain is equal to the diversity order. So equation 1.14, okay, this equation demonstrate what we set out to show, which is that diversity gain is equal to diversity order. This is a general property that holds for many types of modulation schemes, in Rayleigh fading with Mesmer ratio combining. Okay, for which types of modulation schemes? Okay, let us review a table. Okay, table 1.2. For the modulation BPSK, okay, binary modulation with coherent detector and orthogonal signals, and QPSK with gray coding. Okay, a MIMO system is said to achieve full diversity when ND is equal to GD is equal to NT times NR. That is, the diversity order is equal to the diversity gain and is equal to the number of transmit antennas times the number of receive antennas. MIMO systems achieve diversity through the use of space-time coding, which we describe in later chapters. Okay, next we will go to section 1.6, Introduction to Spatial Multiplexing. The second class of MIMO techniques that we study in this course is called spatial multiplexing. So the first class is the spatial diversity. This section provides a brief introduction to that topic. Okay, so first let we look at section 1.6.1, the concept of spatial multiplexing. Okay, spatial multiplexing SM refers to transmitting multiple data streams over a multiple channel by exploiting multipaths. Okay, the meaning of the exploit is to use or employ. By so doing, multiple data channels are able to be transmitted simultaneously over the same frequency band. Okay, that is, at the same time and at the same frequency, enabling potentially large numbers of bits per second to be transmitted per hertz of spectrum. Okay, so we do not need more bandwidth to transmit our data. And this is the bits per second per hertz is the unit of the spectral efficiency. Spatial multiplexing is analogous to other more common types of multiplexing schemes, such as frequency division multiplexing (FDM) and time division multiplexing (TDM). In those schemes, multiple signals are assigned to either frequency slots in the case of FDM or time slots in TDM. Okay, in SM, multiple signals are assigned to different spatial channels instead of time or frequency slots, so the signals are transmitted at the same time over the same bandwidth. As a result, SM does not suffer from bandwidth expansion the way that TDM and FDM do. Okay, why do we have a bandwidth expansion in TDM and FDM? Okay, for example, I have the time slot 1 second now. But in this 1 second, I need to transmit 10 different data strings. So I need to divide the 1 second time slot to 10 smaller time slots. Okay. After doing this, I will expand my bandwidth to the tenfold. Okay. So the required bandwidth is about 10 times compared to the original bandwidth. And for FDM, for example, I have one data string to be transmitted, and I need a bandwidth of 10 megahertz. However, if I want to transmit 10 data streams at the same time, then I will need 10 times 10, which is equal to 100 megahertz bandwidth. So the FDM also suffer from the bandwidth expansion to the 10 times. Figure 1.10 shows a high-level block diagram of a SM MIMO system. Okay. Figure 1.10 is a generic diagram of a MIMO communication system that uses spatial multiplexing. Okay. First, we have some data strings which is needed to be transmitted. Okay. We can transmit up to the minima of NT and NR data strings. Okay. Why? We will prove it in chapter 3. Okay, and then we input these data streams in a precoder. And the output of the precoder are NT transmit antennas. Okay. And these NT transmit antennas will transmit the signals into a scattering rich propagation channel. And at the receiver, we have NR receive antennas. And after receiving the signals, we will pass the signals through a postcoder. And at the output of the postcoder, we will have the received data strings. So as illustrated, there are three main components to an SM system: the precoder, postcoder, and the channel. Okay, this is precoder, this is the postcoder, and this is the channel. The first component is referred to in the diagram as a precoder. Its purpose is to map the multiple input strings of data that are to be transmitted onto the set of transmit antennas. The simplest form of precoder simply maps each data string to a single unit antenna. This, of course, can only occur when the number of data streams is equal to the number of antennas. Okay, for example, if I have 10 data strings and I have 10 transmit antennas, okay, then I can directly map the data strings to these transmit antennas one by one. In general, the number of data strings may be less than or equal to the number of transmit antennas. In the general case, the rule of the precoder may be more complex. One type of precoding that we study in Chapter 3 is called eigenbeamforming. Okay, in that scheme, the operations of the precoder depend on the characteristics of the communications channel. The second component of an SM system is the postcoder, which processes the signals from the receive antennas and generates estimates of the original input data streams that originally went into the precoder at the transmitter. Okay, since the signal at each receive antenna consists of the sum of the signals from each of the transmit antennas, the postcoder must be able to, in its sense, strip off each data stream from the composite received signal. Okay, what is stripped off? Okay, the meaning of this phrase is to separate. Okay, separate each data stream from the composite received signal. There are various ways to do this, which are discussed in detail in Chapter 8. The third component of an SM system is the communications channel itself. In order for spatial multiplexing to work, the channel must have a significant amount of multipath scattering. Okay, this may seem odd. Okay, the word odd here means strange. Since multipath is normally regarded as the enemy by communications engineers, since it degrades the performance of conventional communication systems. Okay, the word degrade means make something worse, and the word conventional means the traditional. However, since spatial multiplexing exploits multipath, its presence is necessary for SM techniques to work. In Chapter 3, we discussed the concept of channel rank and show why it is used to characterize the scattering richness of a multipath channel. Okay, in fact, we will model the MIMO channel as a matrix H, and the channel rank is equal to the rank of the matrix H. The spatial multiplexing literature uses a variety of different terms to describe the data signals that are able to be transmitted at the same time over an SM MIMO system. Terms such as data streams, data pipes, and spatial channels are common terms used to describe these data signals, and they mean the same thing. In addition, when eigenbeamforming is used, the data signals that are transmitted in parallel are often called eigenchannels. Okay, when you see eigen, this word, eigen, what would you think about? Okay, if you remember in linear algebra, we have learned eigenvectors and eigenvalues. So the eigenchannels are related to the eigenvectors and eigenvalues we have learned. It can be shown that the maximum number of data streams, n string, that can be supported by a MIMO system using spatial multiplexing is given by n stream is equal to the minima of nt and nr. This equation shows that for an n by n MIMO system, the throughput increases linearly with the number of antennas. Okay, since the increase in the number of data streams does not require a wider bandwidth, the equation shows that the spectral efficiency of a MIMO system also increases linearly with the number of antennas. Okay, figure 1.11. Okay, let us see figure 1.11 in the next page. Okay, figure 1.11 is the theoretical capacity of an N by N MIMO communication system in Rayleigh fading. So the x-axis is NT equals to NR is equal to N from 1 to 10. And the y-axis is the theoretical capacity in bits per second per hertz from 0 to 90. Okay, there are 4 curves in this figure. First is the SNR is equal to 0 dB. Okay, it is this curve. Okay, the second one is SNR is equal to 10 dB. Okay, and is equal to this curve. The third one is SNR is equal to 20 dB, is this curve. And the fourth one is the SNR is equal to 30 dB, is this curve. Okay, we can see that when N is larger, the theoretical capacity is also larger. And when SNR is larger, okay, 0, 10, 20, 30 dB, the theoretical capacity is also larger. And furthermore, we can see that these curves are actually straight lines in this figure. Okay, so figure 1.11 shows the theoretical average communication capacity in bits per second per hertz. Okay, here is a red star. Let us see this red star. Although communication engineers often use the term capacity in such a way that it has units of bits per second, it is also common to define it to have units of bits per second per hertz. Okay, in that case, theoretical capacity is equivalent to theoretical spectral efficiency. For this discussion, we have made this assumption and used the terms interchangeably. Okay, what is the meaning of interchangeably? It means that we sometimes use the term theoretical capacity, and we sometimes use the term theoretical spectral efficiency, and they are the same. These distinctions are clarified in Chapter 2. Okay, in Rayleigh fading plotted as a function of the number of antennas when NT is equal to NR for different signal-to-noise ratios ρ. This plot illustrates the linear dependence of the average capacity on the number of antennas. Okay, you can see that this is the theoretical capacity. This is the number of antennas, and they have a linear relationship, which is one of the key properties that has led the wireless industry to enthusiastically adopt MIMO techniques in its modern wireless standards. Okay, the word enthusiastically means that we have a hard heart. Okay, these results show that even at modest SNR values, it is theoretically possible to achieve spectral efficiencies of 15 to 30 bps per hertz. Okay, back to figure 1.11. Okay, this is the line, okay, at the 15 bits per second per hertz, and it is the line at the 30 bits per second per hertz. We can see that between these two red lines, okay, the number of antennas is equal to 2 and to the to 10. Okay, so we just need to need a reasonable number of antennas to obtain the high bits per second per hertz. That is the high theoretical capacity. Okay, it is evident from this plot. That is, means this plot gives us evidence that the capacity is proportional to the number of antennas. That is, C of n, this is the capacity, is equal to A of rho times n, where A is the slope of the curve, which is a function of rho. Okay, you can see that the slope of the curve is a function of rho. Okay, where NR is larger, the slope is also larger. It follows that the capacity of an n by n MIMO system, C MIMO or MIMO of n, is n times the capacity of a SISO system. That is, C MIMO of n is equal to n times C SISO. Okay, where C SISO is the capacity of a SISO system. It should be emphasized that these results are theoretical and assume ideal scattering in the channel. That is, we have a large amount of the scattering paths, and the different paths are independent in the channel. In practice, maximum spectral efficiencies are significantly lower than these values due to the combination of implementation limitations and the presence of ill-conditioned channels, which we defined in Chapter 3. Nevertheless, the utility of the theoretical results in Figure 1.11. Okay, let us see Figure 1.11. Okay, this figure. Like any theoretical communication capacity predictions, is that they show what can be achieved in the ideal limit, and they provide a reference to judge how much room there is for improvement in practical systems. Okay. Next, let us look at the section 1.7, open and closed loop MIMO. Okay, MIMO techniques normally require that either the transmitter or the receiver have knowledge of the characteristics of the communications channel. Okay, MIMO techniques are often classified as either open loop or closed loop, depending on whether the transmitter or the receiver uses knowledge of the communications channel. MIMO techniques that require the transmitter to have knowledge of the channel are called closed loop, because they require the receiver to estimate the channel and to send that information back to the transmitter, hence requiring a closed loop. Okay, let me plot a figure to you. Okay, this is the transmitter. Okay, and this is the channel. We use H to denote the channel. And this is the receiver. Okay, then this is the output of the receiver. Okay, If the transmitter need to know the channel, then the receiver will do the channel estimation and feedback the channel information. Okay, this it is 25 minutes. Okay, see you next time. Goodbye.